Okay, so I'm going to go and start. It's 2:45. Hello, everyone. My name is Taher. I'm Taher Chegini. I'm a PhD student at the Civil Department, and my advisor is Dr. Hongil Lee. And my primary research focus is on urban hydrology, but today I'm going to discuss a set of tools that I developed over the course of my PhD that are related to urban. I'm going to kind of discuss the package itself, and then I'm going to show you some of the applications, the way that I've implemented them in my PhD. Can you guys hear my voice okay on Zoom? Or should I get closer?
You're good.
It's okay. Yeah.
Great. So first of all, let's talk about geospatial data. Probably most of you heard about it, but just to make sure that all of us on the same page, I'm going to very briefly go over what do I mean by geospatial data and what is the importance of this type of data in especially in my field in hydrology. So geospatial data, usually when we talk about geospatial data, we are talking about information about some certain features that they should contain geographic positions of that data points that are available. So there are usually a combination of data from various sources, and they are linked by their geographic positions on the map. So for example, if you take a look at the image on the right, this was developed by the Center for Information Resilience, and it's about a map that's the current events that are happening in Ukraine and the invasion of Russia to Ukraine. So what they did is that they developed the map and they used some open source material data from, for example, Twitter to gather some data, right? For example, videos and images, and then they try to map out the events that are reported by the users on those freely available websites, and then they try to use satellite imagery to make sure that the data are correct, and they are going to show the results on the map. So, for example, you can see here that let me use the mouse here. So you can see here that, for example, the green ones are the ones that are military activities, and the orange one are the places where there are some explosions reported in that location. So you can see here that these type of data are, if they are provided in a timely manner and they contain vital information, they could be really useful for people that don't have access to these type of data quickly. And for example, ordinary people that are in that kind of danger zones, they can kind of try to get some information about there, or some journalists that are available there. So these are the things that can really help these people if they can have access to this type of data in a timely manner. So, and there are two primary forms of data in geospatial data. First, there are vectors, which are points and lines and polygons. For example, if you look at the map here, the markers and also the polygons are the ones that are a vector format. And then there are raster format, which are pixelated or gridded cells, and they contain, for example, satellite imagery. In this map that you see here, the base map, which includes the data related to where there is ocean, or there is water, or there is land, or there are some green areas, that's where the data are in the raster format. So you can see here that for this kind of a simple application, all sorts of data are merged together in order to provide us with the information that we need for this application. So now let's see what's the application of this geospatial data in hydrology, which is my field. First of all, we know that 71% of Earth's surface is water, and then out of the 71%, 95% of the water are in the ocean. But in hydrology, we're mainly focused on the fresh water. So we can see here that out of that 71%, only 2.5% is fresh water. And out of that fresh water, we can see here that almost 70% of that is related to glaciers and ice caps. and 30% are the groundwater. And in the field of hydrology, especially urban hydrology, that is my primary focus. I'm more focused on the surface water, on the surface freshwater. So out of that 2.5%, 1.2% is the one that I'm more interested in. And again, out of that 1.2%, we can see here that about 70% is again ground ice or permafrost, which is not the focus of my study. And I'm mainly focused on that, the remaining part. So you can see here that if you kind of multiply all these percentages, these 30% of 1.2% of 2.5% of 71%. So it seems that like it's really a small kind of percentage of data. Essentially, if you look at the map on the right, this is where the land is. And the primary focus of especially urban hydrology and hydrology in general is that we are more focused on the land part. What are the processes that are happening in the land part? So now let's focus on this land part a little bit and then see what type of data we need in order to do some analysis on this portion. So you can see here that in the land part, what we have, first of all, we have precipitation, right? This would be all our input data that are coming from the atmosphere toward the land. And then we have some evaporation, evapotranspiration, that the water from the surface is going to evaporate. And then some parts of the precipitation is going to infiltrate into the soil. And some part of it is going to be flow over the land, which is called a surface water flow that we have. So as you can see here, with this relatively kind of simple water cycle that we are seeing here, we need quite a bit of data. First of all, precipitation. Precipitation is one of the most important data that we need, which is basically the input to our model. But it's also one of the most difficult data to get right. And there's a lot of uncertainties related to precipitation. And still, we haven't been able to solve this issue of precipitation. So the precipitation data that we get are from, for example, in situ measurements, or there are some radar data. When you combine all of them, again, you cannot get a really good sense of or accurate measurements of precipitation. So that's the first part of data that we need. And then the second part is because the water is going to infiltrate into the soil, then we need some information about the soil itself. What is the type of soil? Because that's going to determine the speed that the water is going to infiltrate into the soil. And then regarding evapotranspiration, we need information about energy, like what is the radiation waves that are occurring in that area? What is the moisture contents of the atmosphere that are occurring in that area of interest that we have? And then once we have that, then we come to the last part, which is the surface flow. For the surface flow, what we need, the data are related to land use, land cover, or like the river network that are in the region of our study. So you can see here with these, although these sound like simple processes, but in order to model them correctly, we need quite a bit of information. And all of them are available in different formats. And they are not located in a central area and in a central kind of repository that you can access and get the data. Then you'd have to kind of process all these data separately and then try to overlay them, because if you recall from the previous slide, in geospatial data, you overlay data from different sources in order to provide the information that you need. So here is the same story. You get precipitation, energy data, soil data, all of them you need to overlay because these are geospatial, but you need to overlay them to get the data, to get the information that you need for your modeling. So now let's see how we can retrieve the data. This is the traditional way of retrieving the data. For example, let's say that we need data from 4 sources. We need like river network, we need some street data or building data, vegetation, and also then we integrate these type of data. In order to get this data, first we need to, usually you have to get the full data set, the entire data set. You need to get the entire data set that includes, for example, the street network. Then you need to subset the data to the region of your study. If you're studying, for example, a simple city, or you're studying a region, a large area, or maybe you're doing a global study. So you need to subset the data based on the region of your study. And usually these type of data are relatively large. They could be gigabytes or terabytes of data. Therefore, if you want to process this data and subset them, you need to have some powerful workstation, right? You need to have access to those clusters, so you can kind of subset the data for the part that you need. And then the next part after subsetting is that you want to store the processed data, do your analysis, and if you want to publish them in some peer-reviewed journals, then you'd have to provide them with the information that you're going to use in order to do your analysis. And that part would be you need to upload them to a remote server and give access to the people that should be kind of seeing the results. So you can see here that it's a really tedious process. It involves lots of steps and requires workstation. So it's a time-consuming process, and there are some difficulties again related to publication. If you want to publish a reproducible and extensible research, then that becomes very difficult, because when you publish your code and you want to publish your data, if your data is really big, then if the user wants to process the data into another region, then they have to do all the steps again themselves. So the reproducibility is something that's very missing in this type of, when you deal with the traditional way of retrieving the data. So now that we know what are the disadvantages of using this traditional method, let's think about how we can kind of address these issues that we have. So let us look at it this way. So for example, all of us are students, and we usually cannot afford to get one of the workstations like in our personal our home for your personal use. So we usually use the cluster in the university, or we ask our advisors to provide us with such workstation that can handle this type of processes, right? So we go to them, we spend some time, we get the data, and then we move the data to our laptop, which is like a 800 laptop, which cannot do much, but you can kind of do the processing for those kind of subset of the data that you have. So that's one option that for us students is available. But there is another option that we can use in order to do the same operations. And that involves the same steps, but instead of doing that, we can kind of take advantage of the cloud technologies that are available, the iCloud, and if you you heard about them, like Google Colab. So these are all of the cloud technologies that are available for you to use. But the issue with those is that if you want to do your operations on those, they could also be very expensive. If you want to run some of these operations on, for example, Google Colab, then you'd have to pay for extra, because the free version does not provide you with the required kind of time and also the computational power that you need. Therefore, you need to pay for them. But there is another option that's available and is totally free. You can do even more than what we talked about up to now. You can do even more than that, and then all of them are free. But then you might ask, why, if this option is freely available, why it's not widespread, why it is not mainstream, why not many of us have heard about it? And that option is called a web service. So first, let's see what the heck is a web service, and then we talk about why it's not mainstream at the moment. Based on World Wide Web Consortium, the official definition of web service is that it provides a standard means of interoperating between different software applications running on a variety of platforms and or frameworks. So I know what you're thinking. That was the first time that I read this sentence. After provide, everything was Greek to me. So now let me break it down to you. Assume that in the vastness of the abyss, there is a dark, cold room at the end of the hallway, and that room is called a server, a data server, at least the bottom one that you see in this figure here. And the only reason that, and in that dark room, there is a computer, not really in a traditional sense that it has keyboards and like monitors, but there is some computer that's doing some stuff. And the only thing that it's doing is because it creates lots of noise and it has some blinking lights. So, and you don't want to deal with that dark room, and you don't want to deal with the server man John if you're a fan of Silicon Valley. So now the next thing you do, you go to the next room. Your next room is where this API is. So you look at the room, it's really open. You can see some people there, and you open up the door, and then you see a bunch of nerds, opinionated nerds sitting around there. And then once you enter there, you want to say that, here is my issue. There are lots of data on the server. I'm afraid to go to that room. Provide me with some information. How can I access those data? So the reaction of there is that first they say that, how dare you enter my domain? And then they say that, well, now that you're here, you need to do as I say, right? Because I'm an opinionated person, then everything that I do is the correct way of doing it. And therefore you cannot tell me what to do. I just deliver what I think is the best way for you to receive the data. So after a couple of minutes, they get back to you and they give you something called, for example, a JSON file. And before you even can ask them that JSON what, and then they're going to shut down the door, shut the door, and then so you're going to left with a file that you don't know what to do with. So that's the main issue that we have in web services, that it's technically very difficult, it's very involved. There are lots of components and information that are available that you need to deal with. You can see here that some of the jargon here that I don't want to bore you with the meanings of those jargon, but at the end of the day, we are the client. We are having some like laptops, or we have our phones, and we want to use this data. So the way that we want to deal with it is that there are some standards that you need to follow if you want to use the data. So I'm going to go over some of the details, not too complicated. I just want to give you the gist of what's happening. For example, let's take Google Map into account, right? So you open up Google Map, and then you enter a query. You want to search for a restaurant, for some restaurant of something, right? So you're opening like a map viewer here. And then once you type a query there, you're going to ask for some geospatial information, right? Just show me all the restaurants there. Then what's going to happen, and the kind of the back end of the Google Map is that it's going to send a query into the server. For example, it could be a WFS query. It's going to request for some feature from the data on the server, and then it's going to kind of do some from the data service, it's going to do the query, and then there are some processes that are happening. So for example, you requested data for a region in a bounding box, then it's going to get all of the data in the bounding box. And then the processing part is going to say that, for example, what type of restaurant is it? Is it just a bar? So it's going to kind of provide some additional information about those data. And then once you get that, then it's going to kind of go back to the user and say that this is the data that you requested. It's going to provide it on the Google Map for you to kind of look at and get more information. So we as users are only in the first part, right? We are only in the map viewer or in the client side. So we are not exposed to all these complexities that are within the web services available. That's the main issue that we have, that us as scientists, if we want to use that, we don't want to use the map view. What we want is we want to have access to this web service, to this, for example, WFS, to this WCS, whatever they mean, right? Because these are the parts of this ecosystem, these standards that provide us with the information that we need in order to do some kind of scientific explorations. So we need to find a way in order to get past all these complexities and difficulties that there are in the kind of web service standards. Another thing is that hosting these web services are really costly. It's not that you can, as a junior student, you cannot go and host a web service yourself. The cost of using these cloud technologies are really high. So that's why most of these web services are provided either by the governments or like private companies. And if you want to go with the private companies, then you have to pay a fee, again, which is not an option for us. But luckily, especially in the US, there are many sources of information that are freely available but they are in these kind of obscure formats of WFS, all these JSON files and stuff. And we, as scientists that are non-CS, not computer science, we have some difficulty to deal with. And that's where kind of my packages kind of help with that. What's going to provide for you is that it's going to be the middleman here. It's going to take care of all these complexities and then provide you with a unified API to access many of these web services that are available. And the software stack that I developed is an open source, is freely available on GitHub. And there are like 7 Python packages. So obviously, if you want to use it, you need to have some knowledge of Python, Python programming skills. And these 7 packages each one of them are standalone. So you can use them separately. You don't have to install all of them. So you can use them separately based on whatever the needs of your project. So there are some low-level packages, and these are the things that I've mentioned. They're going to deal with all those complexities, like the WFS, WMS. So it's going to take care of all those complexities that are available in the standard. And then there are some high-level ones. These are the ones that usually the users, the scientific kind of community are would be more interested in, because here you can have access directly to the data that you need, right? So this package has been very well received in the community, and it's been installed 170,000 times to now. And people are kind of really interested in the type of service, because it's especially in the Python community of hydrology, it's a unique package that no one has ever kind of developed before. So that's why kind of many of the scientists are kind of eager to use that. It makes a lot of things easier for you. Let me give you some examples. For example, let's say that you want to get all the dams in the US that their storage capacity is more than 200 acre-feet, right? So you can see here with just a simple line of code, you can easily get all the data that you need with just only one line of code. So you don't have to do anything related to, you don't need to know if it was WFS, you don't need to know if it was WMS, you don't have to have any knowledge related to the web service. But under the hood, it's using all those freely available data. For example, this National Inventory of Dam, US Army Corps of Engineering is the one who is kind of maintaining the service. They have a RESTful service. Then I connect to that and then get the data based on the query that you need. You can just simply say, find me all the dams that the max storage is between 200 and 5,000 acre-feet. It just returns the data as geospatial data. Then you can kind of plot the data as you need. Or for example, let's say that you want to find all the USGS stations. These are the stations that provide you with, for example, a stream flow data, like what is the velocity, what is the height of the water, or some other data that are available in USGS stations. So you can see here again, with just 2 or 3 lines of code, you can have access to all sorts of data related to those stations. That's why it's really convenient and intuitive, and can help save you lots of time regarding kind of preparing and getting your data based on your query that you need. These are some other examples. For example, on the left-hand side, you're seeing the data related to groundwater recharge. For example, in this case, you see here that we did a query over the whole US. But in this case, we are doing it over a watershed. For example, I don't know, Braze Bayou or Buffalo Bayou. These are the kind of smaller scale watersheds, right? So you can get the data, the river network, you can get river network, you can get a groundwater recharge information, or this one is a watershed in Hudson region. This is the data on the right top is the land use land cover data. Is, for example, what are the type of vegetations, or what are, if it's an urbanized area, if it's an open space area. So you can get all of these information from the land use land cover data set over the region, again, with just a simple line of code. Or you might be interested in getting the elevation data or slope data. These are things that are quite easy and intuitive to retrieve the data, again, using those web services. So you can see here that the hardware package takes care of all those complexity and provide you with a simple and intuitive API for you to request the data that you need. Now, let's see how we can kind of use let's see how I use this package that I developed in the field of in my kind of research, in my PhD research study. So as I've mentioned, I'm mainly interested in urban hydrology. I'm mainly interested in urban hydrology. One of the the first thing that we are interested in urban hydrology is related to flooding, right? That's one of the things that we are mostly interested in because of many reasons. Because in urban areas, that's where most people live. So that's why we are very interested in trying to figure out what is the dynamic of the climate in that environment. And also another important aspect of it is we want to do this analysis in larger scales. We just don't want to focus, for example, on a city, on Houston, right? We want to, because as I've mentioned previously, although the land is a very small part of the hydrological cycle, the water cycle or the earth, but it has a huge significance. It has a kind of huge impact on the global climate. So that's why trying to have a good sense of what is the largest scale impacts of urban hydrology plays an important. We want to make sure to account for the impact of climate change in urban areas. We want to kind of find if there is any correlation between the two. Or on the other hand, we want to kind of study what's the footprint of urban areas in the global climate. So these are the things that are really important for us to kind of figure out. And in recent years, there have been many these kind of extreme events of flooding events in Germany, in China, in Houston in 2017. We've experienced all these extreme events. So it's really important for us to have a good sense of what's happening here and how we can improve them, right? So we want to figure out what are the issues and the ways that we can improve them. There are some knowledge gaps. First of all, there's data scarcity. It's the data, although there are many data available, like the ones that I mentioned, but when it comes to urban areas, there are some very important missing data that are not available in larger scale. And for example, the data that are related to the below ground, like the storm drain networks. These are the things that are not really either publicly available, or if they are available, they are not of good quality. And then another knowledge gap there is that when it comes to larger scale modeling, there is no kind of a physically based model that can take into account the effect of larger scale urban hydrology in global climate, which again is one of the results of the data scarcity in urban areas. And in urban areas, there are kind of many elements that are kind of man-made, right? And we don't have enough information in order to capture the impact of their impact into our analysis. And as I've mentioned, one of the most important missing information are the data related to this storm drain that are mainly below the streets in urban areas. So what I did here is that I used the concept, which is called the urban, here we call it a USN, Urban Stormwater Network. So it means that there are different elements in the city that are going to take care of the stormwater that's from the precipitation. They're going to take care of conveying this stormwater safely to some location, to sort of dumping points that are not going to kind of adversely impact the streets or the functions that the street have. For example, if it's a residential area, we want to make sure that whatever stormwater comes, it can safely be conveyed towards some points that are not going to impact the urban functions. So then we are going to use the data that we have from the above ground data, because as I've said, there are the data above ground are ubiquitously available, especially like over the US, we have really high quality data. So now we are going to use those data in order to estimate whatever is the below ground data. And there are a couple of kind of packages and sources of data that I received the data. For example, I'm using the street network data in order to get the vector data over the kind of the street network distribution over some region of a study. And then I'm going to use the high river packages that I developed to retrieve all the geospatial data that are available over the urban areas, like the one that I mentioned, land use, land cover, and then we have some elevation data and also building footprints. These are the things that are freely available over the US. So these are the tools that I use in order to develop this kind of algorithm. And I use two other packages in order to perform some complex network analysis on the data, because the street network data, they are all vector data. And then we are going to kind of carry out some network analysis on those data in order to estimate the below ground data. And in this sense, I'm using a concept called Betweenness Centrality. You don't have to really worry about what does it mean, but our final goal, our purpose is that to go from this street data that we have over the surface and then try to figure out what are we try to kind of weight all of these streets in a sense that say that, for example, the street that is along the university, if it's important than some alley in some other places. So we want to kind of provide a significance factor so a relative significance factor for you to compare the importance of the streets when it comes to conveying rainfall. So that's what this step does. It just gets all the data that we have, land use, land cover, building footprints, and the type of road. And then we are going to kind of say that which street is more important when it comes to conveying a stormwater flow. And this is at the end of the day, this is what we want to do. We are going to start from a street map. This is an actual street map somewhere in California. And then we are going to apply this algorithm, get all those data that are available and combine them into a map that you see on the right. You can see here that instead of having those lines that are, instead of having those curves, now we have some straight lines, right? But what we did here is that we took into account all of the impacts of the parameters that we discussed, like land use, land cover, and all of them, and then converted them into just one variable. So we are saying that this line that connects the two, and each one of these lines are a street, right? And they have a direction. This is based on the slope of the street, we say that this is street, this is the slope, the stormwater is going to go from here to here. Now we have this line, and then we add other information in order to provide some information about the importance of each one of these streets in conveying the stormwater flow. And we want to also validate the result, right? Because at the end of the day, after we estimate the below ground network, we want to have some way of validating the results to say that how good job we did. So and the way that we do it here is that we take whatever is the available kind of the below ground data. For example, Houston and a couple of places over the US, they have some below ground data available. I found some data in Houston, some data in Baltimore, and Snohomish in Seattle, and also San Fernando Valley in Los Angeles. These are the places that they had relatively good quality existing below ground data. So I wanted to use my algorithm to estimate the data based on the above ground data, and then compare them with the existing below ground data to see how good job is doing. So these are the cities that I mentioned: Houston, San Fernando Valley in Los Angeles, Baltimore, and then Seattle. These are the 4 cities that I selected for the analysis. So you can see here, this is the results of this study. And the green ones on the right, the green lines are the available USN data, are the available below ground kind of data here. So the green ones are the ones that my algorithm were able to successfully kind of capture, and the red ones are the ones that my algorithm missed. And in order to have a kind of the model performance over the whole region, what I did is that I rasterized the vector data. What it means is that I took a 1 kilometer by by 1 kilometer grids. And then within each grid, I compared what is the length of existing data to the length of the approximated or estimated USN data. And here is the results you can see here on the left bottom. This is the model performance. You can see here as it gets closer to the red, to yellow, it means that it's really doing a good job. And another way that we also want to take into account is the quality of the street data, because we are using a data source called OpenStreetMap, and this data is publicly available and free. But the downside of this data is that the quality of the data is not the same everywhere. For example, in Snohomish, when you compare it to Houston, the data quality is really bad. I'm going to show you some examples later on. But the data quality of the streets is something that we need to take into account, right? Because a street is the basis for our approximation. If the quality of the street is not good, it means that the quality of the output of our algorithm is not going to be better than the quality of the street data. So these red these red pixels that you see in the kind of upper left are the places where the quality of street data is not good, right? So these are the places that I'm going to kind of skip when I want to compute the final model performance, because I know for sure that the data in those red pixels are not good quality. But you can see here that in Houston, we have relatively good street data. And here is the result for San Fernando Valley. We can see again that the street data quality is relatively good. We have a few kind of red pixels here. And then when you look at the model performance, it's not as good as Houston, but again, most of them are close to yellowish colors. And you can see the results of the estimated network. But then when you go to Snohomish in Seattle, then you can see here that the street data quality is kind of really bad in many of the places, especially kind of when you go to this area. And you can see here that because the street quality is not really good, then therefore in these areas, the percentage of the coverage is not good also in that case. And also we did the same analysis for Baltimore, and the street data quality again is not as bad as Snohomish, but it's relatively good. But you can see here, but there are still some missing data. You can see here that I forgot to mention that the data that we have here for the yellow line, the blue lines are the ones that my algorithm kind of approximates the storm drain network over the whole area, but these are the kind of data that are available. So you can see here again is doing a decent job in those areas as well. So this is just a summary of the results. So what I did in order to get these covered values is just to take the average of all the pixels, percentages of pixels. Take an average, that would be the kind of you're considering as the model performance for that specific region. You can see here that for Houston, it kind of did the best. It was able to capture 74% of the available or the existing USN data. San Fernando Valley was 72, again, very close to Houston, and Snohomish and Baltimore are the ones that are lower than the other. But again, for all these four places, the results were more than 60%. So just to summarize what we discussed today is that first of all, I kind of demonstrated the High River package, the 7 packages that are available in the High River software stack. They provide you an easy and efficient way of accessing many of the high quality and peer-reviewed hydroclimate databases. I don't include any database that the quality I know is not good. So I try to make sure that the data sets that I select and provide access to the ones that are from really reliable sources and the quality is reliable for research purposes. That's what's important. We want to make sure that from a researcher standpoint, they have the highest quality. So that's the first thing. And then it also facilitates publishing and sharing reproducible and extensive research. For example, if you do your analysis for some region, because the way that the algorithm, that the Hydrology is intended to be used is that you use those functions and then you provide your geometry or your bounding box, right? So that's the function. We just provide, for example, some bounding box for Houston. And if another person, another researcher wants to extend your study into another place, they can simply replace the values of the bounding box, right? The latitude and longitude. So we just simply changing the latitude and longitudes. They're going to be able to run the same process, run the same algorithm that you develop in your research for another area. So it's really easy to extend it to other areas. And as I've mentioned, it's easy because it's extensible, it's also really easy to reproduce the results. And most importantly, you don't have to share the data. If you just share your code, because Hydrology is going to directly connect to the server and get the data, so you don't have to, for example, if your data is after a process is about like 2 gigs or like 1 terabyte, you don't have to share the data. The user is going to run the model once, and then they're going to have the same exact data that you produced during research without having to give them access to the data. You don't have to transfer the data. So that's one of the things that really helps with having a reproducible and extensible research. And then we presented results of our novel algorithm for estimating urban storm drain network using only publicly available data sets. We didn't use any private data in our analysis. We wanted to make sure that all of the data are freely and publicly available to everyone. And then we showed that these, especially the USN estimation algorithm, provides very good necessary tools for researchers to do analysis in urban areas, because that's the one of the kind of the big missing pieces of information in urban areas has been this urban stormwater network. So having that is going to help to do some further analysis at larger scale in urban areas. So that's what I had for today, and I'd be happy to answer any questions.
So we are talking about quality of the data and like kind of like how you're showing it with the red dots and stuff. What was the basis or like the main criteria that you're using to determine the quality of the data?
Discrete data. So the way that we try to estimate that is that we looked at the grid of 1 kilometer by 1 kilometer, right? So theoretically, the below ground network, which runs below the streets, the length of these two, kind of the length of the below ground network should not exceed the length of the street network, right? Because that's the purpose, that you want to, that all the below ground network, most of them for the most part, they are going to run through the streets. So if in some areas, the length of the existing USN, existing below ground data is larger than the street data, it means that there are some missing street data in that pixel. So if the value, it doesn't necessarily need to be 1. But what we are doing here is that we are saying that if the ratio, if this ratio is larger than 1, it means that for sure there are some missing information in that area. But the actual value might be 0.7 or 0.9, right? We don't know exactly. Again, we need a lot more information that is not publicly available. But if it's larger than 1, we are sure that there are some missing information in that area. Anyone on Zoom? Oh, I'm seeing there's a. Oh, so the question here is that is the API able to deal with rate limits? So the web services that I provide access to, they don't have any rate limit. Instead of a rate limit, they have a limit of the number of features that you can request each time. For example, let's say that in the data that you want to request, you're requesting for 20,000 data for whatever the feature is, right? And the service has a limit of 1,000 data. So you cannot request at one time, you cannot request for 2,000 data. But what HighRiver does under the hood is that you request for 2,000 data, then it's going to first check what is the limit of the service, the web service, what's the limit. So it reads the information about the web service, and it notices that, for example, the data has a limit of 1,000. Then it's going to break down that 20,000 request into 1,000 pieces. And then is going to merge the data and then return it back to the user. So that's how HighRiver manages the rate limit, the feature limit, essentially, not rate. Sure. Any other questions from Zoom or live audience here?
Have you thought about like extending this package to like other data applications?
Like
Other than hydrology data?
as long as the data are available in the kind of the web service protocols, they are called. For example, these WFS, WMS, and RESTful, these are called web service protocol. As long as they follow those standards, it should be able to, it can handle those. Because as I've mentioned, there are two categories of packages. There are 3 packages that are low level, and you can use those to access any source of WFS, WMS, or RESTful. It doesn't care what's the data that are available on the server. As long as they follow those protocols, you can handle that. For example, in the case of in the urban hydrology analysis that I did, the data that I used for urban footprints were available from the data is developed by Microsoft, and then it's available via some WFS service. So I didn't provide like an API like the other packages, but I used those low-level kind of packages in order to access that data. So at the end of the day, the only question is that if they adhere to the standards of the protocols. Sure. Sure. If you want to, and as I've mentioned, as I've said, because these are all kind of freely available on GitHub, if anyone kind of requests for additional like web source, data sources that are maybe useful for the community at large, I would be happy to kind of add those features. I've had some people requesting for some features, and if it was something that I think would be kind of useful for other people, I've added it to the package. So if you have something that you're interested in, you can open an issue on the GitHub page in HighRiver, and I will try to see if I can include it.
How do you make a judgment on if the data set is high quality? So, going and looking at every page.
Right. So it's because of the data sources that I use. I only use the data that are produced by the government. For example, they have access to historical data, and they have kind of many people working on these data, and because it's provided by the government, by law they should be public, right? So what they do is that they provide some of these web protocols in order to users can have access to those data. But one issue is that the reason that it hasn't been kind of really adopted by the scientific community is that the main purpose of those web services are mainly for map viewers. For example, ArcGIS does lots of these map viewers, or wherever some sites that you go, for example, Houston has an urban kind of a street network, and also a storm drain network available. You can go, and then you can kind of check out all the data that are available, that are publicly available on a map. It's an interactive map. You can kind of zoom in, zoom out, and then check out all the data. So these are the kind of the main application that they had in mind when they kind of use this application, use this kind of web services. But if a scientific in hydrology, they don't have access to those, they don't have the technical capacity to access those data, that's where I provided that, I kind of removed that barrier between that and then accessing those publicly published from the government side. There are some private, not government-related data that are available. Because I wasn't sure about their quality, that's why I didn't include them. So I only went for, because I have a kind of network of people in USGS and other kind of locations that we are in the same kind of web services kind of community. I usually kind of ask around, see if there's any kind of new development, if there's any kind of government has published a new sets of data. That's why I usually I'm sure that because I kind of trust those people, they are the ones that publish those data. When they say that it's good quality, then I'm going to include them in the package. Okay, thanks everyone. Thanks for also people on Zoom, and have a good day.